This is section 3.3, modeling data with linear functions. Remember, a linear function looks like f of x equals mx plus b or y equals mx plus b. The important parts are the slope m and the y-intercept b. So, testing data for linearity. If we're going to use a linear model for our data, it would be nice to know, is it really appropriate? Now, even if the data are not linear, you can still use a linear model. So, definition. Given a set of values, x1, y1, x2, y2, x3, y3, and so on out to x sub n, y sub n. So they're n data points. That's what the little n subscript stands for, that you have n data points. We say that, number one, the data are exactly linear if and only if there's a straight line that passes through all of the points. Now, if you have only 2 points, of course it's exactly linear. Remember, you need 2 points in order to graph a line. If you have 3 or more points that's exactly linear, then you actually have something. Number 2. The data are approximately linear or almost linear if and only if the data appear to make a line when plotted. So it's kind of like they almost line up, but maybe 1 or 2 is kind of not with the others. And number 3, the data are not linear if and only if the data do not appear to make a line when plotted. It's kind of like they're just all over the place, or perhaps maybe they're making a curve. They're looking something like that instead of kind of a straight line thing. Now, this thing talks about making graphs with the points. So, definition. Given a set of values, x1, y1, x2, y2, x3, y3, and so on to x sub n, y sub n, the scatter plot, or scatter diagram, is the graph of the individual points plotted on a plane. So you just plot the points. So anytime you just plot a bunch of points without connecting them or anything, you have a scatter plot, or a scatter diagram. Now, if we combine the previous 2 definitions, like the idea of linearity, approximately linear, and not linear, with the idea of the scatter plot, now, we will eventually show you in this section how to get a scatter plot using the calculator. We can make the calculator plot individual points. So, we have the following. Number 1, data are exactly linear if and only if their scatter diagram makes a straight line. So it's kind of like you can put a ruler up to your scatter plot and you can actually see all the points lining up. Number 2, data are almost linear if and only if their scatter diagram looks almost like a line. So again, when you put your ruler up there, you see that maybe it passes through some of them, but not all of them. And number 3, data are not linear if and only if their scatter diagram does not resemble a line at all. Again, maybe they're just all over the place on the xy plane, or else maybe they're making some sort of a curve. So we look at some graphs to illustrate the definitions. So maybe with the actual scatter plots that I'm going to show you, it'll become a little bit clearer what we're talking about here. Number 1, the graph below shows data that are exactly linear. So it's kind of like if you put your ruler up against this, you would actually see that they really are on the same straight line. Now remember, line is y equals mx plus b. So looking at this one, the b has to be -3 because that's the point that's on the y-axis. We can actually figure out the slope from this. If I go right 1 and then up 2, I'm at the next point. Right 1, up 2. So my slope is 2. Remember, the slope is the change in y over the change in x. The change in y is up 2 units. The change in x is right 1 unit. So for this one, we could actually figure out the m and the b. So we'd have y equals 2x minus 3. Number 2, the graph below shows data that are almost linear or approximately linear. It's kind of like if I were to lay a ruler up to this, maybe you could find it going through some of the points, but not all of them. It's kind of like a few of these appear to be, off by themselves, but more or less has the shape of a line. So those data points are almost linear. So we'd be looking for a line that closely approximates them. Now, the line that closely approximates them may or may not pass through any of them. That's sometimes the problem with data that are almost linear, that your so-called best line may not pass through any of the points. And number 3, the graph below shows data that are not linear. Notice they're just scattered all over the place. They don't make any shape at all. So this is just like someone threw some rocks against a wall. Now again, just because the data are not linear doesn't mean we can't use a linear model. It's just that the linear model probably has nothing to do with the data. So we would like to have a test that will let us know which of the 3 cases we have. in order to state the test, we need some definitions. So we'd like to be able to do the test just by applying it to the actual numerical values. We want to be able to bypass the idea of graphing them. Now, for some reason, these definitions and notation that we're about to introduce, they're not in your book, and I don't know why. They really should be, because they are the standard notations and definitions that help us determine whether or not we have exactly linear, almost linear, or not linear at all. So, Part A, differences. Now, given a set of values, x1, y1, x2, y2, and so on out to x sub n, y sub n, we have the following notation. Number 1, delta 1x is equal to x2 minus x1. Delta 2x is x3 minus x2. Delta 3x is x4 minus x3, and so on. Notice the subscript on the delta matches the second value. The subscript on the delta matches the second value, and so on like that. Remember, the delta stands for change in. So this is the change in the going from x1 to x2. So it's kind of like the first subtraction problem. Again, notice it is a subtraction problem. If we were to lay this out in a table of values, to calculate each one of the delta x's, it's always right x minus left x. Right x minus left x. Okay, now if we have these for the x's, we also have them for the y's. So for number 2, delta 1y is y2 minus y1. Delta 2y is y3 minus y2. Delta 3y is y4 minus y3, and so on. Again, notice it's still right minus left. The subscript on the delta matches the second value. It's always right minus left for the delta x's and the delta y's. Let's try an example. So consider the following points. P1, coordinates are 2, 6. P2, coordinates negative 4, 3. And P3, coordinates are 5, negative 7. So this is like x1, y1, x2, y2, x3, y3. We're going to find the following. And number 1, delta 1x. Number 2, delta 2x. And number 3, delta 3y. So our solutions. For the first one, delta 1x. Remember, that's going to be y2 minus y1. Excuse me, x2 minus x1. So negative 4 minus 2. You get negative 6. For number 2, delta 2x. That's going to be x3 minus x2. So 5 minus negative 4. We get 9. For number 3, delta 3y. That's going to be y4 minus y3. There is no y4. There's not a fourth point. So y4 minus y3 is not possible. We could also say it does not exist or it's undefined. But the subtraction is not possible because we don't have a fourth point. Definition. Given a set of values, x1, y1, x2, y2, all the way out to x sub n, y sub n, if all of the delta I x's are equal, so if you look at delta 1x, it's going to be equal to delta 2x, it's going to be delta 3x, and so on. Whenever that happens, we actually say that the x's are uniform. So if all the x's are the same distance apart, we say it's uniform. Then we have these definitions. Number 1, the first differences denoted by delta 1 yi. So the I ranges from 1 to n for the y. Delta 1 y1 is y2 minus y1. Delta 1 y2 is y3 minus y2. Delta 1 y3 is y4 minus y3, and so on. The 1 on the delta stands for the first difference. And again, notice this subscript on the y matches the second value in the subtraction. And again, it's always right minus left. If you look at this very closely, the first differences are really the delta 1y, the delta 2y, the delta 3y, and so on that we had before. If we have first differences, we can have second differences. So the second differences, denoted by delta 2yi, and again the 2 stands for second differences, is given by delta 2y1 is delta 1y2 minus delta 1y1. Delta 2y2 is delta 1y3 minus delta 1y2, and so on like this. The second differences are the differences of the first differences. Excuse me. So excuse me. The first differences, you simply look at the differences in the consecutive y's. The second differences, you look at the differences in the first differences. If we have second differences, we're going to have third differences. So the third differences, and they're denoted by delta 3yi, they're actually the differences in the second differences. So delta 3y1 is delta 2y2 minus delta 2y1. Delta 3y2 is delta 2y3 minus delta 2y2, and so on. So again, the third differences are the differences in the second differences. The second differences are the differences in the first differences. And the first differences are simply the differences in the consecutive y's. And we have so on like this for higher order differences. Now, a lot of this should become a little bit clearer when we try some examples. And also, there's an easy way to calculate them. So the easiest way is actually with a table. Okay, we're going to illustrate that in our next slide. Okay. Now, it's very easy to make a mistake in these, and once you've made a mistake, if you calculate more differences based upon that, the mistakes can just propagate throughout your table. Because the first time I did this with the slides, I actually did have a huge mistake, and that made me go back and correct a lot of things. Hopefully in the class notes, I didn't make any mistakes with those. So you might want to check my simple subtraction, because that's really all it is. It is just subtraction. So, as an illustration, I'm going to calculate some differences for the following table of values. Okay, my x's 0, 4, 8, 12, 16, 20, and 24. My f of x's 13, 9, negative 7, 10, 13, 17, 19. Now, you are supposed to first observe that the x's, they are uniform. That is, to go from one x to the next one, you add the same value. So notice, all my delta x's are 4, right? 4 minus 0 is 4, 8 minus 4 is 4, 12 minus 8 is 4, and so on. So I am able to start calculating some first differences. So this row is delta 1. These are the first differences. Okay, these little lines just let me know which values did I use. Remember, it's right minus left. 9 minus 13 is negative 4. Negative 7 minus 9 is negative 16. 10 minus negative 7 is 17. 13 minus 10 is 3. 17 minus 13 is 4. And 19 minus 17 is 2. So again, this row right here, these are my first differences. They're also just the delta yi's. So again, each entry in the delta 1 was obtained by taking the value that is diagonally up and to the right minus the value that is diagonally up and to the left. Okay? So remember, it's right minus left. Okay, now from these values, if I look at their differences, again, right minus left, I'll have a row for delta 2. So now I have my delta 2 row. Negative 16 minus negative 4 is negative 12. 17 minus negative 16 is 33. 3 minus 17 is negative 14. 4 minus 3 is 1. 2 minus 4 is negative 2. Notice there are fewer numbers here. So there does eventually come a time where you can't calculate a difference anymore because you've run out of numbers. So again, this row right here are my second differences. And again, we obtain it from right minus left. Okay, right minus left. Okay, from this row, if I calculate their differences, I will have delta 3. So these are going to be my third differences. So 33 minus negative 12 is 45. Negative 14 minus 33 is negative 47. 1 minus negative 14 is 15. And negative 2 minus 1 is negative 3. Again, notice fewer numbers. And again, it's right minus left. And we can keep going like this. So, just for the fun of it, let's go ahead and compute the fourth differences. So, negative 47 minus 45 is negative 92. 15 minus negative 47 is 62. And negative 3 minus 15 is negative 18. And again, right minus left. So remember, it's always up and to the right minus up and to the left. This table, if we actually were to just write the y's without this functional table, is sometimes called a lozenge diagram. Because it's supposed to be that if you look kind of like this thing, it's supposed to make a diamond, you know, like, kind of like a lozenge, a cough drop. So anyway, that's how we calculate the differences. This is probably the easiest way to calculate the differences. Again, remember, you had to have all the x's the same distance apart. So using the differences, now that we've calculated some, again, going back to this, be very careful with your subtraction, because once you've made a careless error, it just carries through the table. So using the differences. Okay, we're going to look at using some of the differences, some of the uses in this section. Later sections we'll see some other uses for it. Turns out they're really the same uses, just in disguised forms. So, theorem. Given a set of data, x1, y1, x2, y2, x3, y3, and so on up to x sub n, y sub n, we have the following. Number one, if the first differences are all equal, then the data are exactly linear. Number two, if the first differences are all approximately equal, then the data are approximately linear. Number three, if the first differences are not all equal and not all approximately equal, then the data are neither exactly linear nor approximately linear. So this is actually an algebraic way to determine whether you have exactly linear, approximately linear, or neither one, given the data values. You don't need to plot them. Okay, now remember, the second differences are the differences of the first differences. So based upon that, we have the following corollary. Because again, the second differences are calculated as differences of the first differences. So corollary. Given a set of data, x1, y1, x2, y2, x3, y3, and so on out to xn to y sub n, we have the following. Number one, if the second differences are all 0, then the data are exactly linear. Number two, if the second differences are all approximately 0, then the data are approximately linear. Number three, if the second differences are not all 0 and not all approximately 0, then the data are neither exactly linear nor approximately linear. As far as whether you use the theorem or the corollary, it's entirely up to you. Sometimes I'll use the theorem, sometimes I'll use the corollary. Let's try some examples. So determine if each set of data are exactly linear, approximately linear, or neither. Notice this is really multiple choice. Okay, you have three choices: exactly, approximately, or neither. So number one, here are my set of values. Okay, so this is my function. Again, do observe that the x's are all the same distance apart, right? I add 3 every time. So our solution. Again, all x values are the same distance apart, so we calculate the first differences. So here are my functional values, right? 47, 49, 51, 53, 55, 57. You can probably look at that and see that the differences are all 2, right? So 49 minus 47 is 2. 51 minus 49 is 2. 53 minus 51 is 2. 55 minus 53 is 2. And 57 minus 55 is 2. My little diagonal lines are really in the wrong place, aren't they? Notice if you wanted to calculate the second differences, they'd all be 2 minus 2, they'd all be 0. But anyway, looking at this, all my first differences are equal. So according to the theorem, the data are exactly linear. And again, these little diagonal lines, I've got them too high, don't I? Okay, number 2, I've given the ordered pairs. So I've got 2, negative 66.25, 5, negative 62.13, 8, negative 58.25, and 11, negative 54.88. So I've got ordered pairs. Instead of having a table, I have ordered pairs. But the idea is still the same. So our solution. First of all, we do observe that the x's are the same distance apart. They're 5 minus 2 is 3, 8 minus 5 is 3, 11 minus 8 is 3. So the x values are all the same distance apart. So again, the word is uniform. They're all uniform. So we're going to calculate the second differences. So I need to put my y values here. So here are my y's. Negative 66.25, negative 62.13, and so on. Okay, so do right minus left. Okay, now I obviously took out a calculator to do this. So you're doing negative 62.13 minus 66.25, and you get 4.12. If you do negative 58.25 minus negative 62.13, 3.88. And negative 54.88 minus negative 58.25, you get 3.37. Notice they're not all equal. So that rules out exactly linear. Now, are they all approximately equal? Well, sometimes myself, in order to see whether they really are approximately equal, I go ahead and calculate the second differences to see if they're all close to 0. So if I do the second differences, 3.88 minus 4.12, negative 0.24, 3.37 minus 3.88, negative 0.51, these are fairly close to 0. So these are approximately linear. Now you're probably wondering, what would be considered not close to 0? Like suppose one of these was like bigger than 1. Okay, that's probably not close enough to 0 in order to be approximately linear. Also, you might want to plot them to see if it looks like they are lining up. But I'm going to go with these are approximately linear. For example, 3, I'm back to a table. So here are my x values, 4, 12, 16, 20, 24. My f of x values, negative 9, 23, 20, negative 11, 7. So our solution, again, observe that the x's are the same distance apart, right? 12 minus 4 is 8. 16 minus 12 is, that's 4, isn't it? And 20 minus 16 is 4. 24 minus 20 is 4. Notice this is off. Okay? So not all the x values are the same distance apart. Okay? So what are we going to do? We calculate the first differences anyway. Okay? So 23 minus negative 9 is going to be 32. 20 minus 23 is 3. Negative 11 minus 20 is negative 31. 7 minus 11 is 18. Notice they're just all over the place. Even if you try to calculate the second differences, notice they're not going to be close to 0 at all. Negative 3 minus 32 is, negative 35. Negative 31 minus negative 3 is negative 28. And 18 minus 31 is negative 49. So they're just all over the place. So they're neither linear nor almost linear. Even though they weren't all the same distance apart in the x's, we can still make, because if I just throw that one out, because notice throw the one that's not the same distance apart, even these guys, they're nowhere close to being equal to each other. So the data are not linear at all, and they're not approximately linear at all. So if we were to plot these points, they would just be all over the place on the xy plane. So again, if this guy that wasn't the same distance apart as all the others, if we just throw it out, we still have these incredibly bad values. So neither linear nor almost linear. So before moving on how we actually find an equation for the line that fits the data the best, we're going to show how to graph points on our calculator. Okay, we're going to go ahead and do that. I know in the book he makes you calculate some of these things using other techniques, but we can actually do it on our calculator. So graphing points on the calculator. So we're going to illustrate how to enter points into the calculator using the following table of values. So I'm going to give you the function defined in the table. So I've got 0, 4, 8, 12, 16, 20 for the x's. And f of x is negative 17, negative 5, 7, 19, 31, 43, and so on. Notice looking at the table, we can kind of get an idea for x max, x min, and so on like that. So we're actually doing a statistical analysis of the data. That means we will need to enter the data using the stat key, okay, the key that's labeled STAT on your calculator. So the values of the independent variable are entered into the location called list1, which is abbreviated as L1. And the values for the dependent variable entered into the list2, which is abbreviated L2. Okay. By default, that is what your calculator does. X values in L1, Y values or functional values in L2. That's the default. So pressing the stat key gives you the following screen. Okay, you've got edit, calc, which means calculate, and some tests. We don't really do the tests, so since we're going to be doing some stuff with our calculator, let me get mine out here. So if I take out my calculator, okay, so again, stat, we're there. Okay, so I'm caught up to where I am. So entering data involves editing the data. So since we're already in the edit, right, by default it goes to edit menu, just press choice 1, okay, and then press enter, you'll get this screen. Okay. Now your calculator may not have it at L1, which means you're going to use your arrow keys and navigation keys to scroll it over to L1. So again, let me get caught up here. So just press enter, and I am at L1, just like I'm supposed to be. So remember, the x values are entered into L1, and the f of x values are entered into L2. Okay, that's the default. That way you don't have to change stuff. You don't have to go in there and do too many button pressing things. So the values are entered into each list one at a time. So after keying an x value, just press enter, and it moves on to the next value. And after you completed entering all of the x values, use navigation keys to move on to L2. So you can enter the y values or the functional values. Okay, so after entering all the values, we get something that looks like this. Okay, let me go ahead and enter those in. So let me get caught up again. Here. So 0, enter. 4, enter. 8, enter. 12, enter. 16, enter. 20, enter. Okay, I'm done with my x's. So navigation key to go to the L2. Okay, negative 17, enter. Negative 5, enter. 7, enter. 19, enter. 31, enter. 43, enter. Okay, I've entered all of my values, and notice they match up. Okay, so you might want to check to be sure that they match up, that you haven't forgotten somebody, or that you've made somebody up. Okay, so I've got my x's and y's given to the calculator. Okay, so we now have to quit the screen. So second mode is quit, and you're back at the home screen. So you're back here. So now we need to adjust our window settings to accommodate the data. Okay, I've chosen the following settings because remember, from the table of values, you can figure out the max and min and so forth. So I'm going to let my x min be -5, my x max be 25, my x scale is going to be 5, y min of -20, y max of 50, and y scale of 5 as well. So let me get caught up again. So quit this, go to window, okay, -5, enter, 25, enter, scale of 5, enter, y min of -20, enter, y max of 50, enter, and a y scale of 5 as well, enter. And of course, whoops, leave those last 3 values the same, and then we'll quit that screen. Okay. So in order to graph the points, we must turn on one of the statistical plots. So the statistical plots are the second of the y equal key. So if you press second y equal to get the following screen. Okay? Notice right now they're all turned off. So let me go ahead and turn to my statistical plots. So second stat plot. Okay, and again, they're all off here. Now, if you're not doing any statistical plots, if any of them are left on, you want to turn them off. So that would be choice number 4, and that would turn them all off. Okay, now, in order to do the statistics or the plotting of the points, you got to turn one of them on. The best choice is the one that's already highlighted, the plot 1. So I'm going to use plot 1 since it's already highlighted. Just press enter, and you're going to get this. Okay, so your first choice is you got to turn it on. So if you cannot see that the on is on, it's actually flashing. So let me get on the calculator here. So choice 1, okay, turn it on, just press enter. It's now on. Now you have these different types of graphs. Okay, we're wanting to plot points. Now do notice X list says it's L1, Y list says it's L2, which is what we want. Okay, if we accidentally put them someplace else, we'd have to change it, and sometimes you forget to do that, and you're wondering, well, where are my data? So the first graph that's highlighted, it's hard to tell, but it's the dots. So if I go back to this, okay, so I've turned it on. Okay, it's hard to tell, but now plot 1 is turned on. Okay. For the type of dot, we want the dots, and that's the first one. Okay. These two right here are called box and whisker plots, and we don't really care about using those because we're not a stat class. So it's already highlighted, so you're just going to scroll on down to the next option. If you want, you can just press enter. And if you like where everything is, like these are the how you're going to make the dots. Do you want this kind of open square, plus sign, a small square, or an actual dot? I like this one because it's the biggest myself. So you can change them to be whatever you want. So now again, remember our X list is L1, which is what we want. Our Y list is L2, which is what we want. So you keep scrolling down until you get everything set up the way you want it. Again, I like to keep my dot to be the biggest one. Okay? So after you do all that, again, you may not have the color option on yours. Okay, some of the calculators I have by hand don't have the color option. This one does. So I'm going to stick with blue. What the heck? So we're now ready to graph. If you want to quit the screen, you can do that, or just go ahead and press graph, and you get this. There are your dots. So now, if you want to have the option of having the grid lines, so let me get out of this. Let me get caught up here. So if I just say graph, there they are. Now I want some lines in order to tell some stuff. So remember that's now again, your calculator may not have the lines. It may only have the dots. So second format, and here's where you can turn the grid off or on. Notice I have the choice of the dots or the line. Now, to be honest with you, my calculators that I have, the actual honest-to-God calculators, only do the dot. I hate the dots. So since I can actually do grid lines, I'm going to do the grid lines. So press enter, and now graph again. Okay, and there they are. If you like the lines, that's fine. If you don't like the lines, that's fine. It's kind of your choice. So again, kind of a side-by-side comparison. No grid lines. Grid lines. Okay. So again, this was the second format, and you would scroll this over to grid line to make the lines, and then you get something that looks like that. Again, the grid lines are kind of nice. And notice, these do kind of line up. Okay, they do kind of line up. So they do seem to form a straight line. So a linear model would be appropriate for them. Okay, so even if the data are not linear or almost linear, it's still possible to make a linear model for the data. It just may not be appropriate to do so, but you can still do it. Now remember, when we actually made the table, the delta x's we can calculate, the delta y's we calculate, which means if the data is exactly linear, we have the information in order to figure out the slope. Because remember, slope is delta y over delta x. So you actually can, if it's exactly linear, calculate the slope, and then you can figure out the b by using one of the data points. So if it's exactly linear, you actually can find the equation of the line that will work. Now in the next section, we will look at that, how to do that in a little more detail, and also how to figure out the best line even if the data is not linear, but only almost linear, and even if the data is not linear at all. So that's reserved for the next section. That's the end of section 3.3.